What if the AI that powers something like ChatGPT, what if it acted less like a computer program and more like, say, a law of physics? Well, today we're going to dive into a pretty radical new theory that does just that. It reimagines AI as a system of interacting particles. And let me tell you, this could completely change how we think about the way these models think.
Okay, so let's start with this wild idea. What if every single word in a sentence wasn't just, data, but an actual physical particle? Imagine that words like king and queen have some kind of gravitational pull towards each other. So what would the rules of a universe like that even be? And what would happen if we just let it run?
And here's the crazy part. This isn't just some sci-fi metaphor. A new paper, written by a team of mathematicians, is proposing this exact idea. They're basically saying that if we really want to get what's happening inside the mind of an AI, we need to stop thinking of it as just code. Instead, we should start treating it like a physical system, a collection of particles that are all interacting with each other. All right, so here's how we're going to break this down. First, we'll look at AI through this new lens. Then, we'll get into the rules of the game. After that, we'll see what happens when those rules play out, the inevitable cluster. We'll connect those particles to actual predictions, and finally, we'll talk about why this whole perspective is such a big deal.
All right, let's jump in. Forever, we've kind of treated these huge neural networks as black boxes, right? We know they work, sometimes astonishingly well, but we don't always know why. This new research, though, it starts to pry that box open. It suggests we should look at each layer of the network not as just a bunch of code, but as a single step in time, like we're watching a physical system evolve right before our eyes.
So the core idea here is to model the whole thing as an interacting particle system. It's a huge shift. Instead of just looking at the input sentence and the output it generates, this approach connects what's happening inside the AI to things we already understand really well. Fields like physics or models of how flocks of birds behave. It gives us a totally new and, honestly, a much more powerful way to analyze what's going on.
Okay, so if we're going to treat AI like a physical system, then what are its laws of physics? What are the rules of the game? Well, it turns out they're surprisingly simple. It really all boils down to just three key components.
First up, the particles. What are they? In the world of AI, these are called tokens. Basically, every word, or sometimes even just a piece of a word, gets turned into a long string of numbers, a vector. That vector is its mathematical fingerprint. It captures the word's meaning. But for our thought experiment, you don't need to worry about the math. Just picture that whole thing as one single particle.
Next, where do these particles live? Well, they're not just floating around in some endless void. There's a standard step in these transformer models called layer normalization, and what it does is, effectively, it puts them all into an arena. You can think of it like this. All the particles are forced to stay on the surface of a giant sphere. They can move around, but they can't get any closer or further from the center. It keeps things orderly.
And now for the most important part, the force, what makes them move. It's a mechanism called self-attention, and it's really the secret sauce of transformers. The best way to think about it is like a very specific kind of gravity. Every single particle pulls on every other particle. But, and this is the absolute key, the strength of that pull depends on how similar their meanings are. So the dog particle pulls really hard on the puppy particle, but it barely even notices the galaxy particle way over there.
So, let's put it all together. Here's how it works. You start with all your word particles just scattered around on the surface of that sphere. Then the process begins. As the data moves from one layer of the model to the next, that self-attention force kicks in. The particles that are similar, like king and queen, feel that strong pull and start moving towards each other. And this just keeps happening, layer after layer after layer. The whole system is evolving with every single step.
Okay, so now we have the rules of the game, right? We've got particles on a sphere, and they're all attracting each other based on how similar they are. So, what happens? What's the end game here? If you let this process run for dozens of layers, with all this pulling and attracting, what is the inevitable outcome?
And this is where it gets really cool, because this is not just a theory. When the researchers actually looked at the data from a real, fully trained transformer, they saw exactly what this physics analogy would predict. Look here. In the early layers of the model, the similarity between all the different word particles is pretty low and spread out. But by the time you get to the end, the final layers, whoa, you see this massive spike. Almost all of the particles have become incredibly similar to each other.
And that visual right there, that perfectly captures the main point of the whole paper.
The researchers put it pretty simply, saying that under these dynamics, the particles don't just float around randomly. No, they have this powerful, unavoidable tendency to clump together into these really tight clusters.
So, what does all this clustering mean? Why does it matter? Well, it's not just some neat mathematical side effect. It's actually the whole point. This clustering is fundamental to how the model makes a decision, how it makes a prediction.
Here's a good way to think about it. When all those particles are scattered everywhere on that sphere at the beginning, that's like the model being uncertain. It's considering tons of different possibilities for what to say next. But as they all get pulled together into one or a few tight clusters, that's the model gaining confidence. It's zeroing in on a very specific meaning, becoming almost certain about a very small group of words that could come next.
This particle view also explains something else that's kind of weird about these models. They don't just instantly jump to one final answer. The paper shows it's actually a two-speed process. First, pretty quickly, the particles form a few separate clusters. They call this a metastable state. So if you ask it to finish the sentence, the best pet is you might get one cluster forming around the idea of dog and another one forming around cat. Those are the top contenders. Then, and this part happens much more slowly, those few clusters will eventually merge into one single point as the model finally settles on its number one prediction.
All right, so let's zoom out for a second. What's the big picture here? Why does it matter that we can think about these super complex AIs as just a simple system of particles playing a game of attraction?
Well, for one, it gives us a completely new language to talk about what's going on inside these things. We can now see that this clustering behavior isn't some random accident. It's the entire point of the self-attention mechanism. By connecting AI to the world of physics, we can finally stop treating these models like some kind of magic black box. Instead, we can start building a real, principled science of how and why they actually work.
And that really leaves us with a pretty deep final question to chew on. Think about it. If something as complex, as nuanced as human language can be understood and predicted by a system that's just particles following these incredibly simple physics-like rules, just attracting and clustering, then what does that say about the fundamental nature of intelligence itself? Are we just scratching the surface of a simple universal pattern that underlies it all?